Let's now try to understand the POLARIS or pole star observation method of obtaining a position line. This is also a very quick and easy method with, with which the position line can be obtained. Does not involve any formulas, not much calculation, and we can obtain a PL very fast using this method. Now, before we go into the stepwise procedure, we need to understand the basic concept, the underlying concept on which this method is based. Now, for this, we need to make a rational horizon diagram. Let's assume our observer is in North Hemisphere, and let's make a rational horizon diagram for him. You can see the rational horizon diagram made on the right side of the screen. At the center of this diagram, we have the zenith of the observer, the point directly overhead represented by alphabet Z. And on the circumference, we have the points N, E, S, W representing the rational horizon of the observer. Our observer is in North Hemisphere in this case. Now, when the observer is in North Hemisphere, the equator will be south of the observer. Similarly, on the celestial sphere, the equinoctial is going to be south of the zenith of the observer. Equator is projected onto the celestial sphere as equinoctial. Observer's position is projected to the celestial sphere as the zenith. So let's show the equinoctial in our diagram. The equinoctial in the rational horizon diagram always passes from east and west points. So let's draw the equinoctial. You have the equinoctial in the diagram now passing from east and west point, and it is passing south of the zenith. Our observer is in North Hemisphere, that's why the equinoctial is passing south of the zenith. The point where the equinoctial crosses the observer's meridian is represented by Q. So you can see the Q point marked in the rational horizon diagram now. Now, since Q represents the equator on the celestial sphere, Z represents the position of the observer on the celestial sphere, this arc of the meridian between Z and Q, the arc ZQ, represents the latitude of the observer. So ZQ being the latitude of the observer. Now let us show the pole in this diagram. The pole is 90 degrees away from the equinoctial. So from point Q, I go 90 degrees away, and somewhere here we will have the North Pole visible to the observer. The observer is in North Hemisphere, so the pole which will be visible to him will be the North Celestial Pole. The South Celestial Pole is going to be below his horizon. South Celestial Pole will be 90 degrees south of the equinoctial or the Q point, and it will be below the horizon of the observer. So we have the pole shown in the diagram now. Let's mark the pole with point P. Now with the pole visible in our diagram, let's now concentrate our attention to arc NP. N represents the north point of the observer's horizon. N point is on the rational horizon, and P point represents the celestial pole, North Celestial Pole. This arc N to P is basically the altitude of the pole, or it is also known as the elevation of the pole. You see, N point is on the horizon, P is the celestial pole, So N to P marks the arc of the vertical circle contained between the pole and the horizon. This is the definition of altitude. So NP is the altitude of the pole, also called as the elevation of the pole. Now, we are aware that this celestial pole is 90 degrees away from the Q point on the equinoctial. We are also aware that the N point, which is on the horizon, is 90 degrees away from the zenith of the observer. So now you see point P is 90 degrees away from the equinoctial, that is Q. Point N is 90 degrees away from the zenith. So the difference between Z and Q will be the same as the difference between N and P. Or in other words, the arc ZQ will be equal to the arc NP. So with this, we come to know that this NP will be equal to the latitude of the observer. In other words, you can say that the altitude of the pole or the elevation of the pole straight away gives us the latitude of the observer. So we get a very easy method to obtain the latitude here. If we can take the altitude of the pole, it will immediately give us the latitude, which is a very simple and easy way. The only problem here is the celestial poles are not lit up. If they were lit up, there was some star or some light there, then we would be able to take their altitude and get our latitude very easily. But unfortunately, the poles are not lit up. But there is one star, special star, which is very close to the north celestial pole. There is no such star close to the south celestial pole, but we have one star which is very close to the north celestial pole, and that star is the Polaris. Other name for it is the pole star. Since it is very close to the north celestial pole, it is called as the pole star. Now this star is having a declination of 89 degrees and 10 minutes. So it is within 1 degree of the celestial pole. So with this star being so close to the pole, if we take the altitude of this particular star, then it can very nearly give us our latitude. So this is the concept behind the Polaris or pole star observation. Pole star being a special star very close to the north celestial pole, if we take the altitude of this pole star or Polaris, it gives us very nearly the latitude of the observer. If the pole star was exactly at the same place where the north celestial pole is, in that case it would give us the latitude exactly, accurately, without any difference or error. But since it is not exactly where the pole is, it is slightly away from the pole, the altitude what we get from the observation of Polaris is also not exactly same as our latitude. There is a small difference between the two. Now this difference which is there between the altitude of the pole star and the latitude of the observer is tabulated in a table in the nautical almanac. We can obtain that difference from there. We can apply that difference to the altitude of the pole star, and once applied, it gives us our latitude. So this is the basic concept behind the Polaris observations. We have the Polaris table or the pole star table given in the nautical almanac, which provides us this correction, which can be applied to the altitude of the pole star to easily obtain the latitude of the observer. Now this correction, which is given in the Polaris or Polestar table in our almanac, is divided into three different parts. Because this correction is variable, it is not a fixed correction, as the Polestar will keep on changing its location. The Earth is moving on its axis, rotating on its axis. Because of that, the Polestar also moves. It has a relative motion. And because of this, the correction keeps on changing. So this correction is divided into three different parts. These parts are known as A0. You can see the A0 correction in this screen. And then later on, I'll show you the next two corrections. The second correction is known as A1 correction, and the third is known as A2 correction. So we will see the Polaris table in detail now, and we will understand how these three different corrections are picked up from the table to be applied to the altitude of the Polestar. Now you see the top part of the table. The table is on page 274 of the selected pages of the 92 almanac. And this table is divided into four different parts. Right now on the screen, you see the topmost part, the first part of the table. Now it is mentioned there, the table is used for determining the latitude from the altitude of Polaris and also the azimuth of Polaris. To enter into this table, we have to enter with the value of LHA Aries. In a Polaris observation, they will provide us with the date and time of observation, and they will also provide us with the DR position. So from the date and time, we will be able to get the GHA of Aries from the almanac. Applying our DR longitude to it, we will get the value of LHA Aries. Every column represents a range of 10 degrees of LHA. You can see the first table is from 0 degrees to 9 degree 59 minutes. Then the second column is for 10 degrees to 19 degree 59 minutes and so on. So there are total 36 columns representing the LHA of Aries. When you enter into any of the columns, you can see, let's say for example, we take this column of 40 to 49 degrees. Once you enter into the column, you will see on the left hand side, the degrees are mentioned. So 0 stands for 40, then the 1 stands for 41, 2 for 42, 3 for 43, that way. Now let's say for example, you want to find out the value of A0 for a LHA Aries of 45 degrees. Then it will be entering into this column, going to 1, 2, 3, 4, 5. So for 45 degrees, the value of A0 is 0 degrees 13.4 minutes. In case the LHA Aries is going into minutes also, there could be an interpolation which is required. To give you an example, let's say the LHA Aries is 005 degree 30 minutes. So we entered into first column, which is from 0 degrees to 9 degrees. So 1, 2, 3, 4, 5. When you go to 005 degrees, you see the value is 19.5 minutes. When you go to 006 degrees, the value is 19.1 minutes. So for 5 degree 30 minute, it will be exactly midway between these two. So in this case, 19.5, 19.1. For 5 degree 30 minutes, the correction A0 would be 19.3 minutes. So you may need to interpolate between the two values if required. This is how we obtain the A0 correction. Let's now move to the second part of the table. If you come down, you will see the second part of the table gives us correction A1. Now this part of the table is entered with the DR latitude, which is given to us in these questions. So you have the latitude mentioned on the vertical axis on the left hand side, and you enter into the same column which you entered in the top part, basis the LHA of Aries. In that same column you come down to the second part, and against the latitude you can see the A1 correction. So there is no interpolation in this part of the table. The maximum difference you will see between two values can be 0.1 only. So no interpolation is required. You can pick up the nearest value. For latitude also, you see the latitude is given as 10, 20, 30, 40, 45, 50 and so on. So whichever is the nearest latitude to your DR lat, that latitude can be picked up without any requirement of interpolation. If you go still further down, you will see the third part of the table now. The third part of the table gives us A2 correction. And this table is entered with the month of the year. So on the vertical axis on the left hand side, you see the months mentioned, January, February, March to December. So whichever month you are taking the site, basis that month you enter into the table, and you follow the same column which you entered basis LHA Aries from the top. The same column is maintained till the end of the table vertically downwards, and A2 correction is obtained by entering with the month of the site. This table also, in the A2 correction also, no interpolation is required. The maximum difference which you see is 0.1. So whichever month you are in, you can straight away pick up that value. No interpolation is needed. Now, after you have obtained the three corrections, the A0, A1 and A2 corrections, the bottommost part of the table, you reach up to the bottommost part of the table, and this part gives you the azimuth of Polaris or the pole star. The azimuth is picked up from this table. Polaris or pole star azimuth is not calculated using the ABC method. We don't use the ABC method here. We can straight away read out the azimuth from the bottommost part of the table. So how do we read it? You keep on following the same column which you entered with basis the LHA of Aries. And once you come to this part of the table, you see this is also entered with DR latitude. You have the DR latitude mentioned on the left hand side in the vertical axis. And whichever DR latitude falls closest to this value, or whichever value is closer to your DR latitude, you enter with that value and find out the azimuth of the pole star. So you can see the azimuth. This is the first page of the table. The table runs into 3 pages. So you can see the azimuth varying from 1.0 to 358.2. So this is the usual variance between the azimuth. Now, one important thing to note here is that if you see the LHA Aries column of 30 to 39, this particular column, you will see that in this column, the azimuth of Polaris is exactly 000.0. That means in this particular LHA range, you will have the Polaris exactly north of you. It will be appearing exactly 000.0. If you go to the second page and the third page, you will see that with the LHA range equal to 210 to 219, 210 to 219 LHA range, you will see that again the azimuth in that range of LHA is exactly 000.0. Now this is significant, this is important. I will tell you about its importance when we plot the Polaris observation. So this is important. Just keep in mind that there are two ranges of LHA Aries, 30 to 39 and 210 to 219, wherein the azimuth is exactly 000.0. In other ranges, other than these two ranges, that is 30 to 39, 210 to 219, everywhere else you will see the azimuth will have some value. Either it will be more than 000, 0.1, 0.4, 1.0, or it will be less than 360, 359.9. It's going up to 358.2. Okay. Now, having understood the table, we are familiar with the values of the table now. We can go into the method, step-by-step method of how do we obtain a Polaris or pole star based position line. Let's first see what is the information which is provided in these questions. They give us the date and time of the observation. The time could be GMT or chronometer. If it is chronometer time, the ambiguity has to be resolved using the AM/PM indication and the GMT obtained. Along with it, they will give us the sextant altitude of Polaris and the index error of the instrument and the height of eye required for dip correction, and they will also provide us with the DR position of the observer. Now the method to obtain the PL, we first calculate or find out the almanac information. GHA hourly value increment gives you the exact GHA of Aries. Once you apply the DR longitude to it, you will get the LHA of Aries. LHA of Aries is what is required to enter into the Polaris tables. Then in the second step, we correct the altitude of Polaris. You apply the index error, you apply the height of eye. With these two applied, you get the apparent altitude and you apply the total correction. Polaris is a star, so you will apply the total correction from the stars table and you get the true altitude of Polaris. Now, once you get the true altitude of Polaris, we have to now apply the corrections which we obtained from the Polaris table. The first correction which we obtained was correction A0, second correction was A1, and the third correction was A2. Now all these three corrections are positive corrections. They are to be added up. So all are positive, all are to be added up to the true altitude. And after adding all these corrections, we have to subtract 1 degree. So true altitude plus correction A0 plus correction A1 plus correction A2 minus 1 degree. If you look at the Polaris table also, at the bottom of the table, you will have this formula given. So the table also mentions this formula, true altitude plus A0 plus A1 plus A2 equal minus 1 degree. And when you apply these corrections and subtract 1 degree as per the formula, you get the observed latitude. Observed latitude is obtained. Now, another important thing to keep in mind that the observed latitude, what we obtain in a Polaris or pole star site, may or may not be your fixed latitude. So how do we determine whether it is our fixed latitude or not? It is basically the latitude from which the position line is passing. So let me tell you how do we find out whether it is the fixed latitude or the observed latitude, and how do we draw the PL on the chart or our plot. So for this, we will need to find out the azimuth of the Polaris, azimuth of the pole star. So let's see how do we obtain the azimuth and then the PL. Now the formula which I mentioned to you is this one. Observed latitude is equal to true altitude plus A0 plus A1 plus A2 minus 1 degree. Now to obtain the direction of the PL, we get the azimuth of the Polaris. The azimuth is obtained from the bottom part of the Polaris table, which we saw just now. Now PL, as usual, the position line as usual in celestial navigation is always perpendicular to the azimuth of the body. So whatever azimuth you obtain from the bottom part of the table, plus and minus 90 degrees to that azimuth gives you the direction of the position line. Now, I told you to keep in mind that there are two LHA Aries values, two columns, where the azimuth of pole star is exactly 000.0. Now, why is that important? Now you see, if the azimuth is exactly 000.0, the PL is going to be perpendicular to it. The PL will be running in east-west direction. If the azimuth is exactly north, the PL also would be exactly east and west. It will be running in the east-west direction. If the PL is running in the east-west direction, then that position line will also be our fixed latitude. Because when you move in the east-west direction, the latitude does not change. So whatever observed latitude you have obtained from Polaris will be your fixed latitude also. But this will happen only in those two particular ranges of LHA Aries, where the azimuth is exactly 0.0. If the azimuth is any other value other than 0.0, then in that case, this observed latitude will not be our fixed latitude. Then in that case, it will be an observed lat, which tells us what is the point, what is the reference point from where the position line is passing. So two important takeaways from here. One, we have found out the direction of the PL, which is perpendicular to the azimuth. Second, we have obtained the observed latitude from this formula, true altitude plus A0 plus A1 plus A2 minus 1 degree. Now with these two obtained, we can now go into the plotting of the position line on the chart or in our answer sheets on the plot. Let's now make the plot of the Polaris observation. Now for plotting the PL, we draw the DR longitude. The longitude used is the DR longitude. The latitude used is the observed latitude, which we obtained from the Polaris site, working out the Polaris site. So observed latitude obtained from the Polaris site and the DR longitude gives us a reference position from where the PL will be passing. Now on this point, we mark off the azimuth of Polaris or the pole star. Let's assume the pole star is here. So the red arrow shows the azimuth of the pole star. and the direction of the PL will be perpendicular to the azimuth of the body. So you see the green color line having arrows at both the ends represents the position line in case of a Polaris observation. Now you can clearly see if the azimuth of the pole star is exactly 0.0, azimuth is exactly north, in that case the PL will be running in the east-west direction, and the PL will then also be our fixed latitude. So this is the plot of the Polaris position line.